Welcome back. Another fantastic week of charged up physics lab. We are continuing our discussion on electrostatics. This week, so last week we talked about how charged stuff interacts. We said that sometimes you have stuff that's positively charged, sometimes you have stuff that's negatively charged. If you have positively charged stuff and positively charged stuff, they feel a repulsive force. If you have positively charged stuff and negatively charged stuff, they feel an attractive force. So like charges tend to repel each other, unlike charges tend to attract each other, opposites tend to attract. This week we're going to quantify that. We're going to say how much do they attract and how much do they repel each other. And what affects that? So we did notice that, so I had my acrylic rod, my magic wand, and when I rubbed this on here a little bit, it had a little bit of an interaction, but really not very much. Like, that's almost nothing. It's really very little. But if I rub it a lot, wow, that's substantially more. There's a lot more attraction when there is more rubbing, which means there's more charge. So when there's more charge, there's definitely more force there. Also, did you notice that when it's way out here, it is interacting a little bit. It's moving, it's wiggling, but it's not really moving very much. But when I brought it in nice and close, now it's enough to overcome that gravitational force pulling it down, and it's enough force to make it swing up. So the closer this gets, the more force there is. So more charge equals more force, but smaller distance equals more force. As charge goes up, force goes up. As distance goes up, force goes down. The farther away, the bigger distance, less force. The closer it is, more force. Does that make sense? Did I say that right, Professor Ashcraft?
I believe so.
All right, that's good. A lot of words, but I want to make sure I put them in the right order for you. Okay, so charge Q1, charge Q2, some distance, we'll call it R, apart, and there's a force between them. This is kind of familiar to me. And Professor Ashcraft, do you talk about universal gravitation in Physics 1?
We mention it, but yes, we've written the equation. Usually we do mg.
So,
Oh,
mg.
but they remember their lab practical.
Oh.
Ooh, yeah.
So, mg is the force of gravity, but it only works when you're on the surface of the planet Earth.
Yes.
If you're somewhere else, it doesn't work anymore.
That's right.
And there's an entire universe out there that isn't the surface of the planet Earth. So we live most of our life here. We spend most of our time here on the surface of the planet Earth, so mg works just fine for most of the things that we do. But occasionally we do need something more universal for the rest of the universe. So the universal gravitational equation says if I have a mass here, m1, and I have a mass here, m2, and they are separated by some distance, we'll call it r, the force from gravity equals capital G, which is 6.67 times 10 to the negative 11.
Mm-hmm.
Hey, I got it on my first try. Times m1, m2, divided by the distance between them squared. If the masses are bigger, that's a terrible one. I'm going to make that better. I'm embarrassed about that. If the masses are bigger, then the gravitational force is bigger. These numbers get bigger, they're up on top of the equation, and that number gets bigger too. But as they get farther apart, that force goes down, and it goes down fast because it's not just r, it's r squared. Mathematically, this form, we have a proportional force compared to the masses, and it's inversely proportional to the square of the distance, the inverse square law, is very similar to what we're going to see from this scenario up here. This scenario up here with our charges, now we're not really considering the masses of them. What we're considering is how much charge they have. And if the charge goes up of either of those, then the force is going to go up. So this force is going to be proportional to the charges, Q1, Q2. But the farther apart they are, I showed with the hanging tape, the farther apart they are, the weaker that force is. So that R is going to go on the bottom. But just like with our gravity equation, that R is going to be squared. It's an inverse square for the distance between them as well. In order to make this true, we need to add a constant. This constant We use a capital letter K for it. If you ever take my upper division physics class on electricity and magnetism, you'll learn that that K is actually made up of other constants. K is actually 1 over 4 pi epsilon 0. You don't need to know that. That's just bonus because it's fun to know stuff. You're not going to be tested on that. I'm not going to assess you on it, but it's just fun to know. We just use the K constant, and it's 8.99 times 10 to the 9th. This was 6.67 times 10 to the negative 11th. This is 8.99 times 10 to the positive 9th. We call this the Coulomb force. Coulomb is a scientist that it's named after, and it's the electrostatic force.
Is he a dead white guy?
I think he is.
Okay.
I think he's French.
Okay.
Charles de Coulomb, I think is his full name. Read up on him. Okay, so mathematically, this formula and this formula are very, very similar. They're dealing with two different things, but they are very similar in their form. We have different constants in front, but we do have some big constant, important universal constant. Big not in size, but in importance. And we have two scalar quantities up on top. In this case, it's mass, scalar quantity in kilograms. In this case, it's charge, a scalar quantity that is measured in coulombs. Down here, we have the distance between them. Again, in meters, it's a distance, also meters up here. Using that, you could figure out what the units for our constants are too. All right, so we are going to test this one out today. We're going to test out Coulomb's law. This equation, the Coulomb force, we get from something called Coulomb's law. It's just the direct proportion, the inverse square proportion. Putting those together, we get Coulomb's law. It's how these charges are going to interact. To do that, we're going to be using logger probe. And Professor Ashcraft's been filming. He's getting bored. I don't want to leave him there doing nothing. You know, he's a man of action. So I'm going to let him jump in here and walk you through the video analysis we're going to do. As, there's a marker, we have a charged hanging object. It's a ball that's charged up. It's got some charge. So it's either positively or negatively charged. We're going to bring another ball attached to a rod, an insulating rod. We're going to bring this in towards it. Now the distance between them is going to decrease. The charge is going to be fixed, whatever the charge is, but the distance between them is going to decrease. If this has the same charge as that, let's say it's positive. If they're both positively charged, this one's going to feel a force. It's already feeling two forces. It's going to feel a force from gravity pushing it down, and it's going to feel the tension force holding it up. And it's at equilibrium when it's just hanging there. But when I introduce this new charge, it's going to feel another force. It's going to feel the Coulomb force right here. We're going to see how that ball moves, and we're going to use that in video analysis, its movement, to determine if this is true. Sound good? You in?
I'm in.
All right, let's do this.
Hey guys, how are you doing? Hope you had a good break. All right, good to see you. Now, what I want to do is I want to show you this one movie. And this is a wonderful movie. What I have here is I got a movie, electrostatic force. I have a charged rod, and what I'm going to do is I'm going to approach another, or I've got a ball on a rod that is charged, and I'm going to approach another ball. I'm going to play this. It's going 2 frames a second. Okay, as I come over, as I get closer and closer, this one ball gets more and more repelled. Now the ball's on a string. The ball is on a 2-meter long string, okay? Now that is taller than Dr. Johnson. Needless to say, it's much, much taller than me. All right, so when I'm far away, I don't feel very much force at all. When I'm nearby relatively, I feel more force. What we're going to try to do today is we're going to try to quantify this. And especially, I want to see if this is a 1 over r function, or if this is a 1 over r squared function, like gravity is. Let's see that one again. Okay, so this is 2 meters from the ceiling. The ball mass is 2.93 grams. Okay, so that's hardly anything. Nickel weighs about 28 grams. That's about the 10th of a mass of a nickel, an American nickel for you Air National students. And this is about like 1 meter in length. Okay, let's play her again. Now this is really hard to do in the classroom because what I find when I try to do this is the ball on the string kind of curls around to get away from it. So I'm glad that we filmed this so everyone has the same data. All right, I think I'm going to stop this for just a second. I'm going to blank my screen. I'm going to turn my light on. And I'm going to look at what Dr. Johnson wrote earlier. Well, he's got lots of good stuff. But you know what? I'm going to erase this picture here. I'm going to erase this here because that's for upper level people. I'm going to erase that. Yeah, gravity's good, but that was last semester, and we don't want to remember last semester, do we, guys? Okay. Here we have that. You know what? We're trying to find out Coulomb's force, and we can measure the R here, but we don't know what Q1 is or Q2 is. And I'm not going to tell you what Q1 or Q2 is. What I'm going to do is I'm going to use a little bit of old-fashioned physics. All right, so if I'm going to do a free body diagram of this guy, and let's say that I have this guy that's a certain mass here, and he's on a string, and the string is on a certain angle right here. Cool. What kind of forces are we talking about? Well, I'm going to do a free body diagram of them. Gravity, yep, straight down towards the center of the earth. Cool. Tension force, okay. It's a rope, so what is the tension force? Well, it's the direction of the rope. Ropes never lie. What's pushing it this way? Is it the wind? No, it's this Coulomb force. Okay, Fc. I'm going to say at this point in time right now it's motionless. So A equals 0. Any other forces? I can't think of any. Can you? All right. So what I want to do is I want to have an X and a Y like this, my standard American one, because that way gravity is going to be all negative Y, Coulomb force is going to be all negative X, and tension we're going to have to break into components. Okay, now this angle is really, really small. How do I know that? Well, I know it's really, really small because this length is going to be 2 meters, 2.000 meters, and this distance here by that movie, I don't know, what is it, maybe 5 centimeters? If it's 5 centimeters, it's going to be 0.05 meters. So theta is going to be small as can be. Okay, that's going to turn into be something that's pretty gosh darn important to us. All right, so let's do our equations. The sum of the forces in the x equals max. Sum of the forces in the y equals may. All right, good, good, good. All right, in the x, positive x, I have the Coulomb force. Good. Positive y, excuse me, negative x, I've got minus ftx, and that equals 0. Okay. For the y, fty minus fg equals 0. All right, good. Fc minus, well, if this is theta, then this is theta. Cool. And this is going to be my ftx, and you thought there were no free body diagrams in Physics 102. And this is going to be fty. That looks like sine to me. Ft sine theta. Good. Equals 0. Ft cosine theta minus mg equals 0. All right. Well, I got two unknowns, one equation, I can't solve it. One unknown, if I know theta, one equation, I can't solve it. Okay. Well, let's solve for ft. Take mg to the other side. Ft cosine theta equals mg. All right. Ft equals mg cosine theta.
Divided by cosine theta.
Whoa! Whoa! Who's rusty from break? Thank you. mg divided by cosine theta. All right. So what I'm going to do is I'm going to plug in this for this. Okay. Hey, first I'm going to throw it to the other side. So I'm going to say that Fc equals Ft sine theta. Now I'm going to put this in for Ft, and I'm going to get Fc equals, whoa, not Ft, I'm going to say it equals mg cosine theta. Why am I putting over like that? Well, now I'm going to put the sine theta down. Because people, what is sine theta divided by cosine theta? Remember back to your friction lab? That's right. Sine theta divided by cosine theta equals tan theta. So my Coulomb force, I don't know what Q1 is, I don't know what Q2 is. I don't need to. It equals mg tan theta. All right. So what is tan theta? Well, for every frame, this changes, okay? This distance changes. But for every frame, this stays the same. Okay. If I'm going to declare this value x for every single frame, and I can measure it because I'm finding the position for every single frame, then what tan theta is x divided by 2. So Fc is going to equal, am I too low, sir?
No, I got you.
All right. mg x. And I'm going to put this like in a little parentheses because with Logopro, whenever we make equations, we put them in little parentheses. Because that's a variable. Divided by 2. 2 what? 2 meters. Do I know what mass is? Yes. It's like 2.93 grams. Make it into kilograms. 0.00293. Times. Do I know what G is? 9.8. Do I know what the well, yeah, times the variable x divided by 2. And that's what your Coulomb force is going to be. Cool? Cool. All right. So what am I doing in the lab? Well, for the lab, part 1 prediction. Consider the diagram showing the two spheres. Will they repel? Sure. Okay. Yeah. All right. We talked about that. We looked at the movie. Yeah. We looked at the theory here. Okay. We did our free body diagram. And what we just did was we just took a look at this and we actually made ourselves a formula for the Coulomb force. And now we're going to do the video analysis. Now, the reason we're doing the movie here is, for some reason, you're not here in class. I'm very sorry about that. You might be off in Europe enjoying yourself. I don't know. But we're going to have some fun here. I'll show you how to do it. Okay, so this is the movie. So what I've done is, this is different than what the directions say. You're supposed to open the CMBL, and in the CMBL, they have this already pre-made for you. This is not a pre-made lab. We have had to do a couple things because of COVID, so this is a little bit different. So what I'm going to be doing here is I'm going to be analyzing the position of two different balls. I'm going to go back to the very first frame. If I go back to the very first frame, what I notice is that the length down the ceiling is 2 meters. You don't see the top of the, well, where the ball is hanging from, it's beyond our ceiling here. Okay. The mass of the ball is 2.93 grams. The mass of the ball is going to be 0.00293 kilograms. Take the 2.93, divide by 1,000, and then you get that. What I've done here is at the very bottom, these little 3 buttons here will, when I press that, it gives me other tools I can use. If I put the cursor on for a while, it will tell me what these will actually do, such as add point, or set origin, or set scale. Hey, what I'm going to do right now is I'm going to set the scale. If I had followed the directions and opened that one file, it would have already set my scale. But here what I'm doing is I'm telling the computer how far a distance is. For example, this is a 1 meter stick. I put my cursor down and I'm going to draw a line that is exactly 1 meter. And then when I lift my cursor up, it's going to ask me, well, how far is that? The default is 1 meter. Now I'm going to say, yeah, it's 1 meter. I'm just going to say, okay. Other times it's going to be a distance other than 1 meter. And that's going to be fine. Okay. Anything else I should do? Well, right here, they have set origin. I want to also do that. And guys, this is a little trick that I have. I'm going to set the origin right along the string. Why am I going to do that? Well, it's going to become a little apparent later. What we're really interested in is the distance that the ball moves from that point on the string, what I called X. If I set my origin right there, whatever distance that is going to become X. In fact, I'm just a little bit off of the string, so I'm actually going to set that again and try to be right on the string. What difference does a pixel make? It might make a difference. Okay, so what I'm going to do now is I'm going to go up to here to set an active point. No, actually I'm going to go 1 frame first. Just 1 frame. Okay, I've got my 2 there. I'm going to set an active point, and my first active point is going to be the rod moving in. I'm going to try to do right in the dead center of the ball, all the way through. Got to make sure that I don't get the old man shakes. So every frame is a half a second. So the guy's trying to come in here at a pretty steady rate. Now you see that the other ball is moving a little bit, but I don't know if it's moving at a steady rate or not. At the start, it didn't move that much, and now it's starting to move lots. If you're wondering what that yellow ball is on the line, that just tells me what my positive x-axis is. I can actually rotate my axes if I want to, but I don't want to. All right, so that's my 13 frames. What I'm going to do next is I'm going to go down to this button, and I'm going to add a second point. So I'm going to add a point series. And now I'm going to play it back all the way. I'm going to go 1, and I'm going to start collecting data on the ball that is coming straight down. Didn't move, so I'm just going to keep it there. Oh, moved very, very slightly. So I'm going to try to just move very, very slightly. Yeah, this thing's hardly moving. I don't want to give it too much movement. But yet I want to give it enough to show that it did move. And it hardly moved. I know, this is as exciting as watching paint dry.
Maybe we have a class of paint drying enthusiasts.
Okay, so what we've done here is we're going to calculate 2 different things. We have to calculate the distance r between the ball centers in each frame. Okay, well, let's see what the data looks like. I'm going to make this a little bit smaller. And if I take a look at my data here, I've got X position. Now that is the ball that was coming towards. And I've also got X2 and Y2 position. First off, I don't care a thing about the Y, so I want to get rid of that. You guys mind?
I don't mind.
All right. So I'm going to go to graph options. I'm going to go to axes options. And I'm going to get rid of that Y. I'm going to get rid of that Y. Done. Okay. Now, there are two different things I want to talk about. One of them is R. And R is the distance between the two balls, such as the distance between this and this, and the distance between this and this. And the second distance I want to talk about is X. And X is the distance between the line, which is 0 straight down, and where the ball is. So X is always going to be the value of X2, because it's X2 position minus 0. But R is always going to be X2 minus X. So for example, if this is, say, I don't know, minus 0.55, 0 minus a minus 0.55 is going to be a positive 0.55. Okay, that makes sense. Where this guy might be, I don't know, like 0.04. And if you're like negative 0.11, then 0.04 minus a minus 0.11 is going to be equal to positive 0.15. Tell you what, let me write the equation down and take a look at it. So what I want to do is I want to, for data, I want to insert a new calculated column. In my new calculated column, I am going to call it R. R between balls. And the short name, I'm going to call it R. Nope, not E, R. R. And I'm going to give it units of meters. And my expression is going to be, I'm going to go to a variable, I'm going to pick X2. And I'm going to subtract X1, or just plain old X. And say done. Wonder what that looks like. I hope it's going to be like 0.55 at the start, and it's going to whittle down to about 0.15. So if I go over to here, if I left click, I'm going to choose R between the balls. Hey, I think I got it. Because it started like at about 0.55 and ended up about 0.15. That's pretty cool. All right. What else do I need? Well, I want to have a calculated column for X. Okay. So I want to do a new calculated column. And I'm going to call it distance ball moved. And my short name is going to be X. And that's going to be in meters. And that's just X2. I mean, if you really want, I can do X2 minus 0 if it'll make you feel happy. All right. Whoa. That's pretty neat. Almost looks like an X squared function. This point's a little funky. That point's a little funky. I got the old man shakes there. Okay, we'll see what happens. Now, what I want is I want an equation for the Coulomb force. All right. And so let's go to data. New calculated column, F Coulomb. And for a short name, we'll call it FC. Units or newtons. Okay. What kind of expression do I want for that? Well, I want the mass times gravity times this, what I call the distance between that divided by 2. Okay. So 0.00293 times 9.8 times, oh, what variable should I use? Distance ball move. We'll say that. Times, oops, excuse me, divided by 2.
Sorry to the viewers, the camera got a little bumpy there for a second.
Okay. All right. So let's see what that looks like. Huh. Okay. So that seems to go up also. Well, that's kind of neat. All right. Now, what they want us to do is they want to sketch the data points that would appear in an F Coulomb versus an R graph. Not an X graph, but an R graph. Well, how do we do that? Well, the way that we do this is we go over to one of these axes, and if you right-click it to the graph options, to the axes options, you can make your thing on the y-axis F coulombs, and on your x-axis here, instead of time, let's make it R, the R between the balls. And let's see what this looks like. Huh. Okay, so what does this tell us? What does this tell us? This tells us that when there's a small distance, you have a relatively large force. They might say, we're talking 0.0006 newtons. Yeah, but that's a lot bigger than, say, 0.0001 newton. And as we go farther away, you get a much smaller force. Okay. Well, we're going to analyze our data. And we're going to analyze our data using Logger Pro's curve fit in the Analyze menu. Okay, so I go to the Analyze, and I go to the curve fit. And I've got all these different things I can do. I can do a linear, quadratic, cubic, quadric, quintric. But what they want me to do is they want me to do an inverse square. Okay, so I'm going to try the fit. Oh, that's sweet. That is sweet. Look at that correlation. 0.989. All right, it's not 1, but it's 0.989. Let's say okay. That's pretty good. You know what? I just want to try something. You and my Dr. Johnson, I'm going to see if it's just an R fit. I'm going to compare that.
I don't mind at all.
All right. Because maybe it's just an R fit. Maybe it's not an R square fit. So I'm going to curve fit. And instead of this inverse square, yeah, right, let's try just the inverse. We'll try that fit. Ooh, ooh, ooh. I don't like this. Oops, I didn't mean that. This is that one, and this is my, you know, I think the R square is much, much better than the R.
I agree.
All right. So let's see if we can even just cancel that out. Yeah, boom, it's out of there. So I think the inverse square law proposed by Coulomb seems to hold the relationship. Now, a couple things you got to think about. And one thing I want you to think about is, what does the theory say? The theory says that we're talking about point masses. Mathematically, what is the definition of a point? How big is a point? Were those two balls infinitely small? Uh-huh. That's what I want to say. So we're making a few assumptions here, and I'm okay with a correlation of only 0.989 instead of 1.00 with that. And also with like the shaky hands and how it hardly moved in the first thing. And if you've ever tried this experiment in real life, just trying to get that thing close to it and having to move a little bit without curling around. All right. Hey, got a question for you. I'm saying that this FC, the Coulomb force, is equal to mg tan theta, or mg times x divided by 2. Or Dr. Johnson here said that the Coulomb force is equal to k q1 q2 divided by r squared. Are they both true? Yeah, they are both true. And we just saw by this graph here that FC does have some kind of constant divided by r squared, because that's what our correlation said. Cool. They have a question there. If I put more charge on each ball, how would that affect A? Let me ask you a different question. If I put more charge on Q1, or if I put more charge on Q2, or if I put more charge on Q1 and more charge on Q2, how would that affect A? Yeah, that's one of the questions that you'll have. Okay. Thanks, guys.